Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host and teacher, Mr. Takeda, and I'm going to teach you some algebra. This is lesson 6.5 on solving exponential equations now. So we've talked a lot about the rules of exponents, we've talked about exponential functions, but now we're going to talk about exponential equations. So these will be equations that use the variable in the exponent. And we're going to do this a couple different ways. We're going to do it, paper way, and then also using a graphing calculator. Okay, so let's take a look at our first core concept here. And basically, this says two powers with the same positive base, if the base is not equal to 1, are equal if their exponents are equal. So this kind of makes sense. So look at this example here. If 2 to the power of x equals 2 to the power of 5, then x equals 5. That kind of makes sense, doesn't it? If this whole power has to equal this power, then these exponents have to be alike. So that's kind of the base idea that we're going to be dealing with here, is that we have to try and get like bases. Even if we start with unlike bases, we have to try to make them alike using our rules of exponents. Okay, so with the same base, these are going to be pretty easy for us. If 3 to the power of x plus 1 equals 3 to the power of 5, then x plus 1 equals 5. The exponents are equal to each other. So in this case, x equals 4. Easy. Over here, if we don't see the exponent, of course, it has an exponent of 1. So 6 to the first power equals 6 to the power of 2x minus 3. Then, of course, 1 equals 2x minus 3. Adding 3 to both sides, 4 equals 2x. Dividing both sides by 2, then x equals 2. Pretty straightforward. And again, like basis here, 10 to the power of 3x equals 10 to the power of 2x plus 3. Then 3x equals 2x plus 3. Subtracting 2x from both sides, x equals 3. With the same base, very easy. Very easy. With unlike bases, this is where you have to put a little creativity into your thinking. You need to be able to restate these things with the same base. So 5x equals 125. Sorry, not 5x. 5 to the power of x equals 125. And then, so I can think of 125 is 5 to the third power, right? And again, so that's 5 times 5 is 125. I'm sorry, 5 times 5 is 25, times 5 is 125. So 5 to the power of x equals 5 to the power of 3. I've just restated this as 5 to the power of 3. And I know that x equals 3, and I'm done. Second example, 4 to the power of x equals 2 to the power of x minus 3. Okay, so I'm going to restate 4 here as 2 squared to the power of x equaling 2 to the power of x minus 3. And then I can how do I take one power and raise it to another power? I multiply those together. So now I have 2 to the power of 2x equals 2 to the power of x minus 3. Okay, so now I've got like bases. So now I know 2x equals x minus 3. And then if I subtract x from both sides, x equals negative 3. Okay. Then the last one, 9 to the power of x plus 2 equals 27 to the power of x. 27, let's look at it this way. I know 9 is 3 squared and 27 is 3 cubed. So I'm going to think of this as 3 squared to the power of x plus 2. I'm going to think of this as 3 cubed to the power of x. Now I can raise a power to another exponent. And so this would be 3 to the power of distributive property 2x plus 4. And this would be 3 to the power of 3x. Okay, so now I've got like bases. So now I can say 2x plus 4 equals 3x. If I subtract 2x from both sides, 4 equals x, and I'm done. Okay, so unlike bases, you got to be a little creative in your thinking and how to get those bases to be the same. And let's look at solving when the base number is an exponent. So now we have to think about how do we think of these things? We need to think of these things as um, powers with the negative exponents. That's how these things kind of get down here, right? It was negative exponents. Okay, so I'm going to think of 1/2 as 2 to the power of -1. So that negative exponent. That's my 1/2. Now I'm going to write everything else in here, just like it was before. Power of x equals 4. And I can multiply these together now, raising a power to a higher exponent. So 2 to the power of -x equals 4. Now 4, I'm going to think of as 2 squared. So now I have the same base. So -x equals 2, so therefore x equals -2. Over here, 1 over 64, I can think of this as 4 cubed, right? So 4 to the power of x plus 1 equals 1 over 4 cubed. So 4 to the power of x plus 1 equals 4 to the power of -3. So now I can just deal with my exponents. So x plus 1 equals -3. If I subtract 1 from both sides, x equals -4. Okay. Now, so those are some equations. Now let's talk about graphing. So if we try to put these into Desmos or into a graphing calculator just the way they are, actually, standard graphing calculators I can't speak about. But for Desmos, if we try to put these in, they're not going to work. So what we can do here is think of these things as two separate equations, kind of thinking backwards with what we did with systems of equations. So since they're equal to each other, I'm going to set them both equal to y. So y equals 1/2 to the power of x minus 1, and y equals 7. Okay, so I'm basically kind of considering these as a system. Now I'm going to open my Desmos graphing calculator, and I'll put these in this way. So y equals, let me put this on projector mode so you can see a little bit easier. Y equals 1 over 2 raised to the power of x minus 1. So there's that graph here. And the other is y equals 7, which is going to be a horizontal line. Okay, so the point of intersection is our solution. What, -1 point. So x equals -1.807. Okay. And let's do the other one. I'm going to clear these here. Oops. Clear these. So I'm going to let y equal 3 to the power of x plus 2. And then y is equal to x plus 1. Okay, so I'm going to put those into the graphing calculator. So y is equal to 3 to the power of x plus 1. And then y is equal to x plus 1. I think this is x plus 2, sorry. X plus 2, yep. And this was y just equals x plus 1. Look what we have here. We have our exponential graph over here. We have our linear graph over here. And they do not intersect. So in this case, what do we think? We think no solution. So for this one, they don't intersect, so we have no solution. Go back over here. No solution. Okay, and that's it. Look how happy Doug is. I will see you in class next time, and have a good rest of your day. Thanks a lot.